if we could get this thing done. All right, so here we go. Conservation of momentum and collision. So a stream of bullets whose mass is 0.0038 kilograms, or 3.8 kilograms, right? So each mass of bullet is equal to, right, 0.00. Oh, I'm sorry. Thank you. Sorry. Thank you. And 3.8 kilograms. Okay. And uh, there are 15 bullets. Okay. So one whole magazine, I guess, right? So 15 bullets with same V. Okay. So a stream of bullets fire horizontally with this much velocity into a large wooden block with mass of 12 kilograms. What is the speed, right, the block will require after it has absorbed 15 bullets? Okay, so when the bullets get embedded inside the block, it's just going to get stuck in there. And then when 15 bullets gets entered in there, right, all the bullets and the block system will start, move. And then what speed will it go after absorb 15, and what change in kinetic energy will there be there? So first thing we should start out is, since within the whole system there's no net external force, so conservation of momentum must occur. So sum of total momentum initial must equal to sum of total momentum final. Okay? This is for all collisions, by the way. All right? Initially, right, there are 15 m bullet times v bullet initial. Or if you want to think of it this way, there's momentum of a bullet times 15 of it, right? You could think of it that way as well. Plus the mass of the wooden block, right? Times the velocity of the wooden block initial. That has to equal to, right, the whole 15 times the mass of the bullet plus the mass of the wooden block times the final velocity of the whole system. Well, we know initially the wooden block was not moving, it's at rest. So it's zero. Okay? And since these are velocities, so it has to be vectors, by the way. So here we have 15 times mass of the bullet, which is 0.0038, times the velocity initial, which is 1100 meters per second. And it is going in the positive direction. So make sure you understand that this has to be, this has to be plus or minus, right? Because it is a vector. And it is positive direction. Plus 0 is equal to, right? Here we have 15 times 0.0038 plus 12, right, times VF. So if you solve this correctly, okay, I think you get your VF is equal to 5.2 meters per second. And it is still going in the positive direction, by the way. Right? So since they want the speed, it's just the magnitude of the VF, which is positive 5.2 meters per second. So that was A. What about B? What was the change in kinetic energy in this problem? Well, change in kinetic energy is equal to kinetic energy final minus the kinetic energy initial. Well, let's find what final kinetic energy is first. Final kinetic energy is all this times 1/2 times Vf squared, right? So 1/2 times 15 m bullet plus the mass of the wooden block, right? Times Vf squared. So 1/2 times 15 times 0.0038 plus 12 times, right? Um, 5.2 squared, right? And I think you'll get something like 163 joules. Then, to find kinetic energy initial, right, we have 1/2 times 15 times the mass of the bullets only, right, times V bullet initial squared, right? So that is equal to 1/2 times 15 times 0.0038 times 1100 squared. And this thing comes out to 34,485 joules, right? So what was the change in kinetic energy? Change in kinetic energy is, right, 163 minus 34,485 joules. So what is that, John? So I get negative 34,322 joules. So what does that mean? This means this is how much energy was taken out of the system by friction, right, and sound, right? So friction is mostly heat, right? So mostly heat, right? So pretty much, right, etc., etc. Okay. All right. Moving right along. I'll post these up so if you have a chance to write it down. I'll have it up there. All right. So momentum and external forces example. They have a lot of these like problems on an AP test where you have a moving train and then there's like something, a load that's dropped onto it while it's still moving. Okay. So something like this is pretty common to see. Okay. So let's take a look at what this was like. Here we have a stream of 2 kilogram masses moving at 5 meters per second, right, is lowered onto the platform below at rate of 2 kilograms every 3 seconds. Okay, so every 3 seconds, you have 2 kilograms loaded onto it, adding onto it, adding onto it, adding onto it. Okay, so the mass is going to get bigger and bigger and bigger. So this is the initial condition. Okay, and this is the final condition. Okay, calculate the initial and final momentum of the particle. Well, so initial momentum, or the sum of all initial momenta, right, is equal to Well, first of all, 4 kilograms, right? That's pretty weird. It says 2 kilograms every 3 seconds, but it's 4 kilograms. I think this might be typo. I mean, this should be 4 kilograms because he's got 2 kilograms. All right, let's just make this 4 kilograms. Okay, it's kind of this is confusing because you got 2 kilograms. So I'm gonna make it 4 kilograms. Is that okay? I think that's kind of confusing that way. So 4 kilograms times, since this thing is traveling with the platform as it's being lowered down, it's 5 meters per second and 5 meters per second for the platform as well. So, okay, it's a positive 5 meters per second plus 10 kilograms times positive 5 meters per second. Okay, so here I have 20 and this is 50, so I have positive 70, right? Kilograms times meters per second xat. Okay, so what's the final? What's the final? Well, sum of all momentum final happens to be here. I have all three objects moving at 5 meters per second with a common velocity. So I have 10 plus 4 is 14. So 14 kilograms traveling at common velocity of 5 meters per second xat, right? And that comes out to positive 70 kilogram meters per second xat. So same thing, it doesn't really change. Okay. So what external force is needed to keep the platform moving at 5 meters per second? None. You don't need any external force. It's just basically going to continue on, right? So no external force needed. Okay, because change in momentum is equal to zero. And since the net external force is equal to change in momentum divided by change in time, it is 0 over delta t, therefore 0. Does that make sense? Right? Because look, change in momentum is final momentum minus initial momentum, so it's 0. So you could write that down if you want to. All right. Now, instead of this 2 kilogram mass is moving at 5 meters per second, it's now moving only at 1 meter per second as it's being dropped. Okay. Now what's going on? So uh, let's make this 4 again just to avoid the confusion. Okay. Because the two kilogram particles are falling down on it. All right. So that's total initial momentum. I have these two moving at 1 and this moving at 5. So I have two separate things. So I have 4 kilograms moving at positive 1 meter per second plus 10 kilograms moving at positive 5 meters per second. So here I have 4 plus 50 is 54. So positive 54 kilograms, right, times meters per second, x hat. Final momentum Here, it's the same thing as what we had before, which is positive 70. Does that make sense? Right? So we're going to just use that positive 70 kilograms meters per second, etc. Is there a change in momentum? Definitely. There's definitely change in momentum, right? Um, and that is 70 minus 54. Therefore, we have 16, right? Kilograms meters, meters per second. So what external force is needed to keep this going at 5 meters per second after those 4 kilograms landed on that platform moving at 5 meters per second, right? There has to be an external force involved. So the, the net external force is equal to, right, change in momentum over change in time, right? So here we have well, let's say we use 3 seconds and we have 4 kilograms coming down instead of 2 kilograms at a time. We changed the problem to 4 kilograms, right? Because we saw this, all right? So here, change in momentum basically is um, um, 16 kilograms meters per second. Divide that by 3 seconds, right? Therefore, um, it's like what? 3 point something, 3.33, 5.33, right? So 16 divided by 3 is 5.33 seconds. Oops, newtons, sorry, newtons, newtons. Now, let's say this was at 2 kilograms at a time every 3 seconds, right? Instead of we changing it to 4 kilograms, let's say 2 kilograms dropped and then 2 kilograms dropped afterwards and another 2 kilograms and so on. Okay. In that case, in that case, we have again change net external force is equal to change in momentum over change in time, right? So the change in momentum, right, is really equal to net change in mv, right, over change in time. So if the velocity stays, right, it's pretty much the same for the 5 meters per second, right? Now, I'm not going to confuse you with this. Let's just stick with this. Don't worry about this, okay? It's going to come out to be the same thing anyway by the time you get the second one in there. So it's not going to really matter, okay? But if you were to just do for 2 kilogram mass, then you could just still work it out. It's just 2 kilograms here instead of 4. And it still works out the same way eventually when you get 2 of the 2 kilogram particles on it anyway. All right. So let's just leave it at that. All right. We're going to do a rocket problem. Okay. I'm going to make you guys into a rocket scientist. Okay. So here we have conservation of momentum. Okay. Now people believe back in the I guess Apollo mission times they thought when they were up there on this in this space, out in like way out in the space between Earth and the Moon. These are NASA rocket engineers who thought this. If you fire the rocket engine out in space, there's nothing to push off of, so a rocket won't go anywhere. Now, can you imagine that? Now, on Earth's surface, when the rocket engine's fired, all that fire is coming out, right? It's pushing off of the Earth. That's why the rocket's going to go up. People, okay, well, all right, well, that's fine. But when you're out in space, there's no platform for the engine to fire off to push the rocket forward. So even if you go out there and you just fire the rocket engine, the rocket's going to stay where it was. But that's completely wrong because it's not like you're pushing off of a thing. It's like if you go up in space and you fire a gun, it will still recoil, right? When you're out in space and you fire a gun, bullet's going to come out and the gun's going to recoil backwards because it has to conserve momentum, right? Well, the rocket fuel is basically microscopic bullets shooting billions and billions of these bullets per second is what's happening when you shoot this rocket engine. Okay, so what's happening is the rocket becomes the gun and it recoils, and that's how the rocket moves because of conservation of momentum. So when rocket fires the rocket engine, it's basically firing lots of bullets, and the rocket itself is basically recoiling forwards. So it will work out in space. All right. Well, the total mass of the rocket is usually going to be, the payload plus, the rocket, and then mostly it's going to be fuel, right? 80 to 90% is going to be fuel. Okay. So as you fire this thing, guess what? You're losing mass. The rocket is actually losing mass. Okay. So here, I'm going to show you that total mass of the rocket is going to be rocket plus the fuel. The initial speed of the rocket that's already traveling is v. This dm is a differential mass of fuel. So this is how much mass is being spent out of a rocket. Does that make sense? Right? So this dm is amount of fuel being spent at the moment. This dm will contribute to how much total mass is going to be lost eventually. Does that make, right? So this dm is amount of fuel spent, which will contribute to negative d big M over dt eventually. This u is the speed of the fuel, or this is actually the muzzle velocity of the rocket fuel coming out of the rocket engine nozzle. Okay? This u is respect to rocket, right? Like the muzzle velocity. Just like the cannon in the cannonball we did, remember? All right. So this is basically, I'm going to just derive it once, so you don't have to go crazy, right? You don't have to keep deriving it. But it's something that you should remember. The momentum of the rocket plus the fuel is equal to the momentum of the rocket plus the momentum of the fuel. So initially, the rocket and the fuel was traveling at initial velocity v right here. So m times v is what we have, right? So this is basically m times v is the initial. The rocket is going to be m, right, minus this amount of fuel being used, right, times the velocity of the rocket that it already possesses plus the change in velocity of the rocket itself, because it's going to increase, right? Minus This small dm, which is the fuel, u minus, remember the cannon one, we had to subtract the recoil of the cannon velocity, right? Same thing. We have to subtract the recoil of the rocket velocity. Okay? So this u minus this is speed relative to with respect to ground or earth. Okay? This is fuel spent. This is the direction of fuel. Okay? All right. So if we curses foiled again, right? We have to foil this thing out, right? So if we foil this, we get all this mess, right? And then if you distribute this thing out, you get dmu and then plus, right? Because negative, negative, dmv, then minus d, what this has to be distributed through. So negative of the minus dv, so plus dm dv, right? This you have to FOIL it out, right? This times that, this times this, and this times that, right? So when you FOIL this out and distribute all this out, this is the mess you get, okay? But notice, this MV and this MV cancels out. This negative DMV, right? And this positive DMV cancels out. And this also cancels out. So the only thing that we have left is 0 on this side, mdv minus dmu. So this is what we have. But this dm is basically negative d big M. How much the mass, the fuel is being spent is same thing as how much the original mass of the rocket is being decreased. The rate of fuel spent is rate of the mass of the rocket being decreased, right? Therefore, if we replace this dm with negative dv, negative d big M, this is what we get, and this is the rocket equation, okay? And this is basically conservation of momentum. So how do I memorize this? This is the way I was taught in college. Ready? Read this with me. DMU, more DV, right? But when you say that, you have to say that with your fist in the air, saying, damn you, more DV, right? Right? You have to say it that way. I guess the people at home didn't see me do that. So you have to do it this. Ready? Damn you, more DV, right? Yeah. So how could you forget that? Right? I even still remember it after all those years when I was learning physics in the cave, right, with the dinosaurs, right? And I still remember it. So you cannot forget that. So, damn you, more DV, right? So this is good to memorize. Okay, so you don't have to derive this every time you use it. At least you should be able to use this equation now, right? All right. So complete that. represents what this is. Okay? So, how do we calculate something from here using this? How do we calculate how much thrust the rocket's going to experience when we actually um, use this equation? And on top of that, what can we actually do to find out how fast the rocket is moving out in space? Because there's no speedometer on the rocket. Like, you can't just like look at a speedometer and say, "Oh, I'm going this fast." You can't do that, you know. So let's find out how much force the rocket is actually exerting, right, by shooting that rocket engine. So since we start out with damn you more dV, we're going to basically divide both sides by dt. Okay. When we divide both sides by dt, right, what we have is, right, on this side, we have m times, remember dv over dt is equal to acceleration, right? So this is acceleration. And here we have negative dm over dt times u. All right? So force, this is force, right? Or otherwise known as thrust. Thrust is equal to, right, negative dm dt times u. This is the muzzle velocity of the rocket fuel, right? This is, right, rate of, right, fuel being spent. Okay? Otherwise known as the burn rate. Right? This is the speed of, right, fuel with respect to the rocket. Okay? That scared me. All right. So this thrust, okay, so F thrust is equal to negative dm over dt u. U is most likely going to be constant because rocket engine is very binary. Either it's full on, it's full off. Right? You just don't do like half U. Okay. So it's like either it's full on or it's full off. All right. Then how do we calculate the speed of the rocket? Well, we start again with damn U more dV. Right? Well, if I multiply or divide both sides by m, right? So I'm going to divide both sides by m. And on this side, I have negative dm over m, right, times u is equal to just dv. If I integrate both sides, here I integrate from mass initial to mass final. Here, when I integrate this, initial velocity to final velocity. And here, this is constant, so negative u, and we already know how to integrate dm over m, so dx over x, it's ln x, remember that, right? So ln m, and we'll evaluate that from mass initial to mass final. That must equal to VF minus VI, right? But, I mean, this is basically V, VF, same thing, right? So if we solve for VF, right, my VF, so if I do this, evaluate this, it'll be negative U, right, times ln m final minus ln m initial is equal to VF minus VI. So my VF is equal to, if I bring this, my initial velocity to the other side of the equal sign, it becomes positive, right? So VI minus, right, U times ln MF minus ln MI. If I switch this, by multiplying this negative through, then I get my VF is equal to VI, right? So if I multiply this negative through, I get plus U times ln MI. Well, let's make it negative then. Negative MF plus ln MI. Okay, if I multiply this negative and negative, then this you can say it as VF is equal to VI plus U times ln MI minus ln MF. Now, finally, my VF then is equal to VI plus U times, by properties of natural log, you can put this in a fraction of ln of mi over mf. This is my final velocity of the rocket. Okay? What time is period over? Nobody knows. All right, let me see. All right. Wow, figure that out. See if you can work on this. On page 22, I gave you, right? I gave you mass of the initial rocket, right? It's over at 36. I only have 4 minutes, so I can't really do another. Yeah, so work on this for the rest of the period because it's got 4 minutes. You should be able to do this. You should knock this out, right? Remember, there are two equations that we should be familiar with, which are this, right, and this, okay? So if you want me to write that up here, so force thrust is equal to negative dm over dt times u. That's one of the equations. And the other one is Vf is equal to Vi plus U times ln of initial mass over final mass. Okay? Yeah, I'm going to post the homework solutions up on Schoology, so please take a look at them. Um, we will finish up this chapter on Wednesday. I know Wednesday is going to be a short day, but I'm going to do my best to finish up my lecture notes of chapter 9 by Wednesday. And it's very important that we know how to do these problems. So, because eventually it's going to help you with rotations, and for those of you who are juniors, it's going to help you with E&M, with Gauss's law and E fields. So, hopefully, there will be no assessment for chapter 9. Okay, there will be no assessment for chapter 9. So, I'll see you guys on Wednesday. All right, try to stay safe, wear your masks, bundle up. It's cold. And I heard we're supposed to get 3 more snowstorms. But it won't affect us. It'll just affect our backs. You know? So we're supposed to get a snowstorm coming in Tuesday into Wednesday, and then Thursday into Friday, and then Saturday. Nuts, I say. So with that note, have a wonderful day. All right. This class is over at 10:40. No, 10:30. Oh, 10:36. So I've got 2 more minutes. All right. I'll stop my lecture here. I'll shut up.